Today we are going to discuss soil density. So to discuss soil density, we need to look at how many particles there are of soil, but also the water and air particles that are in there. At its simplest, density is mass per unit of volume. So how much space does the soil take up and how much does it weigh? So the weight divided by the space, or the mass divided by the volume, equals the density. So the idea here being you have more particles in the same amount of space, you're going to be denser, you're going to be heavier, you're more likely to sink. This is why iron sinks and some wood will float, because the wood is less dense, has more air particles and fewer wood particles. But when we're talking about soil, we often will talk about bulk density, because typically when you're looking at an amount of soil, you're including all of the air particles and all of the water particles that are also in that soil. So when we look at bulk density, we're looking at the density of just the soil particles, not the air, not the water. And this is one of the reasons we oven dry our sample so that we can find out what the bulk density is. So we'll dry out a soil, we'll find the volume of the dry soil, and we'll find the weight of that dry soil. We can also burn a soil in an ashing oven, which will burn off the organic solids, and then we can get a bulk density of just the mineral solids. And then the last point on this screen is that clays have a higher density, a higher bulk density than most other particles because the clay particles are the smallest, so you can compact more of them together into the same amount of space. Sand, because they're larger, there's always going to be more airspace in that bulk density. Then we talk about particle density. So this is just removing all of those air particles and spaces. So we've removed all the water, we're removing all the air now. How many soil solids are there? And we typically do this by water displacement. So we'll look at the weight of that oven dry sample. So that's obviously not weighing any air, and it doesn't weigh any water. So that's the weight of just the soil particles. And then we'll see how much water that soil displaces, because that's just going to show the volume of the solid particles and not any of the air. This is easiest to do with the graduated cylinder, but you guys can do it at home with a jar inside of a bowl, and then the soil that you add will displace the water out of the jar if you fill the jar level, flush. And the water that spills out into the bowl, you can measure that in whatever measuring system you have available to you, or you can even weigh it if you have a scale available to you, because water, 1 milliliter cubed is 1 centimeter cubed is 1 gram. This is a handy little chart I stole from the internet, but I like it because it has pictures. And it's another way of looking at comparing bulk density to particle density. That the bulk density is looking at how much space the soil takes up with the air pores, but without the water. And the particle density is looking at just how much that solid soil takes up and removing all those air particles. And it gives you some general masses and volumes that are often assumed based on what your average soil would have. Any discussion on density leads to a discussion on porosity, because in order to figure out what the bulk density is and the particle density, we need to remove all of the pores. Some soils are more porous than other soils, but basically the soil porosity is how many air spaces there are. So a soil with large granules of sand is going to have more pore spaces in between than a clay with tiny particles that are tightly packed together. Because a porous soil has those air spaces, a wet porous soil means that often those pore spaces are filled with water. And then the adhesion and cohesion means that even in times of drought, you will find water still clinging in between all those pores. Well, at least until it all dries out. But that is where those wet pore spaces is where the biota lives. That's where microbes are hanging out. Average soil porosity, we're going to estimate to be 50%. Sandy soil is obviously much more porous and clay soil is less. So we typically figure out what the porosity is. Basically, it's your bulk density and your particle density, right? So that gives you a percent porosity. 1 minus your bulk density divided by your particle density times 100 because it's a percent. When we talk about soil porosity, we then talk about soil compaction, because as you compact that soil, you push out those air spaces. A porous soil can be compacted quite a bit. This is bad for biota because all the microbes live in those water-filled pore spaces. And all of the larger plants, their roots are growing through those water-filled pore spaces. This is also bad for flood attenuation because soil can hold a lot of water. But if you compact it, you are removing all those pore spaces and the soil cannot hold as much water, and water is just going to flow right over the surface and straight into the waterway. It is good for roads. You want your roads to have a compacted soil base underneath them. It's these pore spaces that fill with water that cause frost heave. So in Northern Ontario, it is really common for the water in the soil to freeze and you get these lumps in the road, which then you drive over, you break those ice crystals, and you cause the soil to compact, and that makes a pothole in the spring. You don't see this with roads that are built directly on compacted soils or on bedrock. It's only in these porous soils that you get these frost heave problems. And it's really good for buildings as well. You want a denser soil will support more of a load. You don't want a porous soil and building a large building on it. That bulk density leads to soil strength. So as you have a denser soil, you typically also get a stronger soil. So as we talked about before, the bulk density means if it has a higher bulk density, it's going to have fewer pore spaces, more compacted. So there's actually like more soil particles to support that tension and stress. So this is why you want a compacted, dense soil underneath a building. And this is why dry, compacted soils are typically stronger than loose and wet ones. So a great example of this are trails. Trails where you have loose soil that fills with water particles becomes a muddy mess. But dry soil that's hardly compacted, the water doesn't sink in it, it's strong, it's sturdy, it's a good trail. Not so good for plants to grow on, but great to support a road or a building. What happens when you do build on top of porous soils is you can get liquefaction, which is ridiculously scary. What happens is those pore spaces get filled with water, and you might think you have a solid soil, but all it takes is a little bit of change in the water pressure and the whole soil can just fall apart. So loose sand that doesn't have any water in it can be compressed. You can pack it together. But water particles, as long as they're at the same temperature, you can't compress water anymore. That's why we have hydraulics. So when you're trying to compress a water-saturated soil, your pressure increases, and a solid soil can then become a liquid mud. This happens, typically there's some kind of like earth tremor that sort of starts this process, but you can just watch like solid dirt become liquid. And I've got a couple of videos that if we were in lecture, I would take some time and watch them. I recommend you guys watching them now. Take a minute, stop this video, go to these links. They are impressive. Sometimes it's just one building that's affected, sometimes it's a whole village. To me, is quite scary. I can't imagine having the ground that you walk on all of a sudden be like quicksand. So the lesson we learn here is that some water is good, but not too much. Because it's nice to have a little bit of water in the soil. Water likes to stick together. So a little bit of water in your soil will help it cohesiveness. But once you get too much, then you start getting that quicksand effect. So I like showing this picture because as a kid, and I think a lot of kids do this, if you put your feet in the sand and sort of squiggle, your feet will go down a little bit into the dry sand. But if you've got damp sand, you can walk on it and it's nice and solid, it's not loose. But if you have wet sand, you can stand on it and squiggle your feet until your feet like sort of disappear down into the sandy mud, and then it's hard to get them back up again. That's like a little mini version of liquefaction. How we test this is with a Proctor compaction test. This is trying to figure out the optimal moisture content, where you can find like the maximum dry density and the maximum wet density. So, and the idea here being that adhesion and cohesion of the water will act like glue and help hold the particles together, but you only want a tiny little bit. And these devices help you discover how much water is the right amount of water. Now we were talking about porosity earlier, and we saw this same picture with pore spaces. When you talk about porosity, some people will start talking about permeability. And permeability, while similar to porosity, is not the same thing. So porosity is how many air spaces there are. Permeability is the ability for water to flow through those air spaces. Permeability is the ability of water to flow through a soil or rock. Depending on the type of rock it is, you don't even need pore spaces. If it is a rock that allows for chemical solubility, you can have a permeable rock that doesn't really have a lot of porosity, but it is still permeable because the water can dissolve and flow through, albeit very slow, but it is still possible. Typically, if you have a very porous soil, you will have a very permeable soil because the pore spaces will connect. But sometimes you can have a super porous rock or soil that is not permeable. So oftentimes, like pumice is a good example. We've seen pumice as children floating on water, and that's because it's very porous, but those pores aren't connected at all. There's solid rock in between all those pores. So it's not very permeable. There is pumice that is permeable as well as porous, but this is to give you an example of how you can have porosity without permeability. And you can have permeability that has low porosity as well, depending on what kind of soil you have. So this is a great example on the side here. We've got cemented sandstone, which has low porosity, and clay with high porosity. But it looks totally different because of the size of the particles. Because clay is tiny, tiny particles, so it has tiny, tiny pore spaces. So here are those same pictures showing that not all things that are porous are permeable. It depends on whether those holes are connected or not. So it's not just the soil type like sand, silt, and clay, but that soil structure also helps. So if you have clay particles, which typically don't lend for a very porous soil, but they're all clinging together in a prismatic structure, water can flow down through the prisms and it becomes quite permeable. But if you have those same clay particles and they have a platy structure, water can't get through as easily. So you have a slower permeability. This is affecting the infiltration rate. And we'll see that in our lab where you can pour water through your soil and time how fast that infiltration rate is. Hi again. So my day went haywire and I'm now filming at an entirely different type of day. It's still the same day, but just in the evening now. But let's get back to this lecture. Hydraulic conductivity is something that people frequently use when they're talking about permeability, or they'll use permeability when they're talking about hydraulic conductivity, but they're slightly different. So we'll measure permeability and infiltration rates as a distance over time, just like we measure hydraulic conductivity, but technically permeability isn't a measurable distance over time measurement. Permeability is just the intrinsic ability of a soil to allow fluids to flow through it. So you can have things that are going to be highly permeable, but we're not measuring that permeability precisely like we do with hydraulic conductivity. The other thing about hydraulic conductivity, it's specifically water. It's hydraulic conductivity. So how fast does water move through this soil? Because permeability can be any fluid, technically. How permeable a soil is not specifically water. We tend to discuss water when we're talking about permeability, but hydraulic conductivity is definitely water. And how permeable a soil is probably the main thing that hydraulic conductivity is going to be measuring, but hydraulic conductivity will change based on the density of that soil and how saturated already that soil is. It's not just the permeability, even though it is mostly the permeability. I included this picture because I found it very interesting how there's obviously some kind of impermeable hardpan here that is stopping the hydraulic conductivity of the soil, where you can see in the first bit that aquamarine color has permeated the first few horizons quite easily and then can't get through that next horizon and has gone down horizontally across, which is a really interesting pattern. This is a handy graphic showing some of the common hydraulic conductivity measurements for known rocks and soils. So unconsolidated materials, so we're looking at gravel, sand, silt, clay, and then solid rocks. Different rocks have higher permeability, therefore higher hydraulic conductivity. And it shows you that things like gravel, which have huge pore spaces and don't stick together very well, doesn't compact very well, shows you that it has high hydraulic conductivity, which we would assume it has a lot of pore spaces. Things like clay, where the particles are really tiny and packed together quite tightly, has a lower hydraulic conductivity, but not quite as low as an unfractured igneous or metamorphic rock, which has practically no pore spaces if it's unfractured. I like how they say that, because once it's fractured, then it's a much higher hydraulic conductivity because the water can then move through those fractures. So different ways we can measure that hydraulic conductivity, or permeability, if you will, depends on what system you have. So we're going to be measuring our hydraulic conductivity by looking at infiltration rate. And we did do this on campus, where we took a ring and we put an inch of water in that ring and timed how long it took for the water to infiltrate down into the soil. That's a measurement of hydraulic conductivity. In fact, it's on our chart here. Some of you, when you're digging your soil pits, found that your soil pit actually went below the water table. So you were having an auger hole style, where you actually were seeing how permeable the soil is. You could time how fast your hole filled in, and you would have learned about the permeability. And then this is what we were talking about before, is the correlations. So you can make inferences about what you think the hydraulic conductivity is going to be based on the pore size and the soil texture and looking at soil maps ahead of time. But you don't actually know what it's going to be until you go out and actually measure those systems. In a future lab, we are going to measure the infiltration rate of our soils we collected from the field, and maybe our radish soils as well might be interesting to measure. And how you measure infiltration rate is you want to measure the rate in which water enters a soil. You can do it small scale in the field, or you can also do it in a lab. When you're doing it in the field, it has to be above the water table, because as we learned, if you're below the water table, the soil is already going to be saturated. So when you do an infiltration rate, you have to be above the water table so the water flows down. This is influenced by two things: gravity, which is constant, but also capillary action. Capillary action, as you probably learned in one of your first year science classes, is that adhesion and cohesion that will pull water down through those channels and into the pore spaces, helped along by gravity. And we have to include both capillary action and gravity as forces that are influencing infiltration rate, because a large pore size is going to have very little resistance to gravity, but small pore sizes are going to have better capillary action. So even though they're resisting the flow gravity-wise, you still have that complementary infiltration of the capillary action, which means just because you have a lot of tiny pore sizes doesn't mean the water isn't going to be able to flow fast. Probably not as fast as something with a really huge pore size like gravel, but there comes a point where the small pores actually help instead of hinder. It is important to remind you and me again that infiltration rate is measuring how permeable the soil is, sort of. It's more of a measure of hydraulic conductivity than permeability. But what it's not measuring is the porosity. Porosity has an effect on the infiltration rate, but it's not measuring porosity in any way. It's measuring hydraulic conductivity, which is kind of measuring the permeability. The process of water moving down through the soil is often called percolation, just like percolated coffee. The percolated coffee water is slowly percolating down through the coffee grounds. Here is an example of measuring infiltration rate in the field, which some of you did on Monday. And here's an example of measuring infiltration rate via an auger hole when your soil sample is below the water table, which some of you also did unintentionally. Infiltration rate is important in real life situations, because if the infiltration rate of the soil is great enough, it can then allow water flow through the soil which can then create channels through the soil over time. You get some erosion. And that is what happened in this particular case that we're looking at here. This is a levee, like from the song, When the Levee Breaks. So this is a man-made hill, and they have a flood wall. Most of the time, you don't need the flood wall. The levee is enough. But then once in a while, when you have really high water levels, it goes up against the flood wall. So this side is protected from being flooded. This is the side with the water. Now, engineers recognize that this piece of wall that is holding back all of this water needs to be supported, that it's not going to support all the weight of all that water. Water is really heavy. If you've ever had to carry a bucket of water, you know this. So they've added what they call a sheet pile down into the levee to support this flood wall, so the flood wall doesn't collapse from the weight of all the water, because the weight of all this gravel and sand pushing down on the sheet pile will stop the flood wall from falling over. The problem is there is a situation where this failed, and I think it's on the next picture. Excellent. So same sheet wall. And what happened was they built this levee, and the natural soil underneath was too, had a really good infiltration rate, I guess is the right word, permeable, too permeable. So the water started to flow down into this soil and then flowed through this soil and started to percolate up over here. And it caused a landslide, and it caused this sheet pile to fail, and the whole levee broke. And if they had measured the infiltration rate of the soil ahead of time, they might have had an idea that this was going to happen. This particular levee might be so old that no one thought to measure it. They just built upon an existing system. But it's one of the reasons engineers care about hydraulic conductivity. It's an important measurement to take and to be aware of before you build a structure. Again, here's another diagram of it. I don't know how to, oh, here's an eraser here to erase all my, so you can see that better. So again, this is the highly permeable soil, and this is the seepage going underneath. And so you have this boiling up on this side. And then this one is showing sometimes you can get seepage going right through the levee, and they call it piping, where the water flow becomes, the soil is so permeable you get an erosion water flow of piping going through. Either way, it's going to cause the levee to not be a levee anymore. While we're talking about soil holding water, let's talk about the water holding capacity. And it's simply that. It's the ability of water, of soil to hold water. We weigh it, we measure it in weight, and it's super dependent upon the pore spaces. You can't hold water without pore spaces. Sand has really big pore spaces, and quite a lot of them. It holds water really well. However, clay also has a lot of pore spaces, and they're smaller. So it ends up being a better water holding capacity than sand because the permeability is not as good. Sand is so permeable, while it can hold a lot of water, it typically flows out again. Whereas clay, with those tiny, tiny small particles, it ends up having almost as much water holding capacity as the sand because all those little spaces add up to as many as the big spaces, and then you don't have the same permeability. This, I think I have this drawing in your lab manual as well, where we talk about water holding capacity in terms of plant growth, where we look at water that is available to plants to use and water that's unavailable, and sort of that limit of the water in the soil. So the idea here is once you go beyond this line, the water's just falling out of the soil. The soil cannot hold anymore. So this is as much water as the soil can hold. This limit here is there's still water in the soil, but it's just a micro amount adhering to all of the particles, and it's so little that it's no longer available for roots to suck up. And eventually you can get rid of that water, but your soil can look pretty dry and still have a little bit of water stuck to those particles, which is why we dry soils in an oven before measuring our bulk density. And you can see here, sand has a much smaller water holding capacity than clay does. And loams and silty loams are best. When we measure water holding capacity, we measure that max amount that it can hold, as well as some other measurements that I was talking about. Field capacity is that max amount. This is the most water a soil can possibly hold. And we express it as theta FC for field capacity. We also have to put in the stipulation that this is at minus 33 joules per kilogram, and this is an air pressure thing. So the amount of water a soil can hold will be dependent on the air pressure. So, which makes sense, but something we need to think about when we're doing this math. We're just going to assume it. We're close enough to ocean level to just assume. Permanent wilting point is sort of like the opposite of field capacity. So in this diagram here, oh, I lost my pen. In this diagram, we have this line is field capacity. And that's what this arrow down here is saying. You guys just can't see it in this particular. This line is our permanent wilting point. So within this space, there is adequate water for plants to grow. Above field capacity, there's so much water in the soil, the water's just flowing through the soil. Below field capacity, there is still water in the soil, but this, I was saying it in a past slide, the word is hygroscopic water. So there's just water that's like adhering to those soil particles. It's still there. There are some microbes that can live in it, but it's no longer available for plants to take in because plants are absorbing water through osmosis. So if there's less water in the soil than in the plant, they're going to lose water to the soil instead of gain it. So this permanent wilting point traditionally was measured based on plants wilting and then not being able to recover again. It's beyond that point where the plant is losing water. It's not getting enough water to survive. It's permanently wilted. It's harder to measure, and we do have a process where we can measure it with plastic cups with holes in the bottom, but it's not an easy thing to measure. It's time consuming. So again, we're looking at our different parts of water holding capacity. Back to that original diagram where I was just talking about the whole thing as water holding capacity, the top line is our field capacity, the bottom line is our permanent wilting point, this is all our water holding capacity. This is what we call available water, plant available water. So the plant available water is our field capacity minus our permanent wilting point. And we use theta to be all of them. So this is available, field capacity, permanent wilting point. I like this drawing where they talk about the permanent wilting point, like there's still water, but you can't access it, like it's below the tap. Thought that was an interesting way to show it. And then here they have, if it's above field capacity, there's a drain here. So like in your sink, if you fill your sink up too high, it starts flowing out that back drain so your sink doesn't overflow. That's above and beyond your field capacity. All right. Putting that all together, our soil moisture content is dependent upon your field capacity, your complete saturation, permanent wilting point, and your hygroscopic drainage. And then here's our totally oven dry, right? So at permanent wilting point, there's no more available water, but you still have water in the soil, that hygroscopic water. Then you're oven dry. Up here, you're at beyond total saturation, like there's not any more water. Here you're at your field capacity, and all of this is just, the more water you put on it, it's all just flowing through. Nothing is staying. And in the middle, we have that capillary water that slowly will drain out, but will actually stay held in the soil for some amount of time. That's where we want our soils to be. That's where they're the most stable. That's where plants are the happiest. Because wilting point is difficult to measure, I have found a table that gives you some average wilting point, field capacity, and available water capacity for different soils. So when you find out what soil you have and you measure your own wilting point and field capacity, you can compare it to this chart and kind of give yourself an idea of where your soil is and your measuring techniques. I'm almost done now. I just want to talk a little bit about groundwater. The water holding capacity of soil is important to us because groundwater is where many places on Earth get their drinking water from. If you have soil that has a good water holding capacity, then it will hold that rainwater and hopefully slowly bring it down into an aquifer in the ground. A lot of people's wells are just dug below the water table into the water that's naturally being held in the soil. So this is, for those of us in the room that aren't geographers, here's our water table, is this line here. And you can see that anytime the land dips below the water table, you get a body of water. And anytime you're above, the water flows down until it hits the water table. And there's a point in the middle where it's flowing down into this water body, but then after the bottom, then it just flows down and it sort of stays down in this fully saturated zone. And if you dig your well down into that fully saturated zone, you're going to have a good source of water. But if you start sucking water out of that well, you can lower the water table and you can lower that saturated zone. And you can, like, eventually any of these bodies of water will get reabsorbed back into the soil. If you're beside an ocean, this can be super problematic because if you take all the fresh water out of the soil, salt water will start getting absorbed and you can ruin your well where you start getting salt water in your well. And this has happened to a lot of oceanside communities. This is the kind of well my mom has. This is the famous artesian well. And this happens when we have aquifers that are sort of hidden by impermeable rock. So what we have here is we have layers of impermeable rock here, and there's a floating piece up here as well. And this is permeable sand or soil of some kind, this yellow stuff. So what happens normally is you have rain that falls, and the water flows down and becomes stored in this aquifer. And if you drill a well down into the water table, you can suck that water up out of there. Sometimes you hit a perched aquifer, which is good too. It's going to have less water in it though. It's not going to last as long. In this situation, these people have gone down, so they're not in their water table, they're in the hidden one. So this becomes an artesian well, because this water table is not what's causing this artesian well to work. The water table for this water, what it's concerned with is the water table for this water. So this is the water table for this aquifer down here. That's what this triangle is showing. So that means that this well, this is where the water table is. But for this artesian well, the water table is way up here. All the water is getting recharged into the soil way up here. This is the water table for this artesian well, which means this well has to pump the water all the way up from here to here. Whereas these guys, gravity will actually allow this water to come to here, so you only have to pump at this last bit. So if you are actually below that water table, you have water springing to the surface. So this is what happens when you have water springs, is you have water springing to the surface because it's below where the water table would be. And if you drill a well into one of these artesian confined aquifers, you can actually have water spewing out. My mom's well has pressure that is beyond crazy, and it's all just from this natural artesian spring. Just wanted to talk about artesian wells while we were talking about water holding capacity. But that is all I have for our density, permeability, water holding capacity lecture. I hope you guys have a good day.